Hey everybody, welcome back to my channel. This is WireDogSec back with another video for you guys. Today's video, we are continuing on with TryHackMe's Cybersecurity 101 learning path. This is the networking module, and this is the networking concepts room. Learn about the ISO OSI model and the TCP IP protocol suite. So hopefully you're all having an awesome day today and ready to learn. Let's go ahead and dive into it. Task 1, Introduction. Have you ever wondered why you need an IP address to access the internet? Is it true that an IP address can uniquely identify the user? Are you curious to learn what the life of a packet looks like? If the answer is yes, let's dive in. This room is the first room in a series of 4 rooms dedicated to introducing the user to vital networking concepts and the most common networking protocols. Networking concepts, this room, networking essentials, networking core protocols, networking secure protocols. Room prerequisites. This room expects that you know terms such as IP address and TCP port number. However, we don't expect that the reader is able to explain such terms in proper technical depth. If you are unfamiliar with these terms, please consider joining the pre-security path. Learning objectives. By the time you finish this room, you will have learned about the following: ISO, OSI network model, IP addresses, subnets, and routing, TCP, UDP, and port numbers, how to connect to an open TCP port from the command line. Get your notepad ready and let's begin. All right. Task 2, OSI model, and let's see what they have for us here. Before we start, we should note that the OSI model might initially seem complicated. Don't worry if you encounter cryptic acronyms, as we provide examples of the OSI model layers. We assure you that by the time you finish this module, this task will feel like a piece of cake. The OSI, which stands for Open Systems Interconnection model, is a conceptual model developed by the International Organization of Standardization, ISO, that describes how communication should occur in the computer network. In other words, the OSI model defines a framework for computer network communications. Although this model is theoretical, it is vital to learn and understand as it helps grasp networking concepts on a deeper level. The OSI model is composed of 7 layers. Layer 1 is physical layer. Layer 2 is a data link layer. Layer 3 is the network layer. Layer 4 is the transport layer. Layer 5 is session layer. Layer 6 is presentation layer. And layer 7 is the application layer. The numbering starts with the physical layer being layer 1, while the top layer, the application layer, is layer 7. To help you remember the layers from bottom to top, you can use a mnemonic such as please do not throw spinach pizza away, or please do not throw sausage pizza away. You can check the internet for other easy to remember acronyms if this helps you memorize them. Remembering the OSI model layers with their layer numbers is important, otherwise you will struggle to understand terms such as layer 3 switch or layer 7 firewall. All right. Another way of saying this is all people seem to need data processing. All right. So that's another way to do it. And let's continue. Layer 1, the physical layer. The physical layer, also referred to as layer 1, deals with the physical connection between devices. This includes the medium, such as a wire, and the definition of the binary digits 0 and 1. Data transmission can be via an electrical, optical, or wireless signal. Consequently, we need data cables or antennas depending on our physical medium. In addition to Ethernet cable shown in the illustration below, an optical fiber cable. Examples of the physical layer medium include the Wi-Fi radio bands, the 2.4 gigahertz band, the 5 gigahertz band, and the 6 gigahertz band. Okay, here's a picture of an Ethernet cable, network cable. All right, layer 2 is the data link layer. The physical layer defines a medium to transmit our signal. The data link layer, i.e. layer 2, represents the protocol that enables data transfer between nodes on the same network segment. Let's put it in simpler terms. The data link layer describes an agreement between the different systems on the same network segment on how to communicate. A network segment refers to a group of network devices using a shared medium or channel for information transfer. For example, consider a company office with 10 computers connected to a network switch. That's a network segment. Examples of layer 2 include Ethernet, i.e. 802.3, and Wi-Fi, i.e. 802.11. Ethernet and Wi-Fi addresses are 6 bytes. Their address is called a MAC address, where MAC stands for Media Access Control. They are usually expressed in hexadecimal format with a colon separating each 2 bytes. the three leftmost bytes identify the vendor. All right, and it says the vendor who build the network interface, in this instance, Intel, right? That's this here. Unique address of the network interface, which is this here. We expect to see two MAC addresses in each frame in real network communication over Ethernet or Wi-Fi. The packet in the screenshot below shows the destination data link address MAC address highlighted in yellow. The data or the source data link address MAC address is highlighted in blue. The remaining bits show the data being sent. All right, so this is what it looks like in a bigger picture here. All right. Layer 3, network layer. The data link layer focuses on sending data between two nodes on the same network segment. The network layer, i.e. layer 3, is connected with sending data between different networks. In more technical terms, the network layer handles logical addressing and routing, i.e. finding a path to transfer the network packets between the diverse networks. In the data link layer, we give an example of one company office with 10 computers where the data link layer is responsible for providing a connection between them. Let's say that this company has multiple offices distributed across various cities, countries, or even continents. The network layer is responsible for connecting the different offices together. The network below shows that computers A and B are connected, although on different networks. You can also notice two paths connecting the two computers. The network layer will route the network packets through the path it deems better. All right, and that's what it looks like here. Okay. Examples of network layer include Internet Protocol, which is IP, Internet Control Message Protocol, ICMP, and Virtual Private Network VPN protocols such as IPsec and SSL/TLS VPN. Layer 4 is the transport layer. Layer 4, the transport layer, enables end-to-end encryption or communication between running applications on different hosts. Your web browser is connected to the TryHackMe web browser or web server over the transport layer, which can support various functions like flow control, segmentation, and error correction. Examples of layer 4 are transmission control protocol, TCP, and user datagram protocol, UDP. All right, remember TCP is a connection-based protocol. All right, so it needs to make a connection, and UDP is basically a fire and forget. So that's used for like streaming services and such, right? And layer 5, session layer. The session layer is responsible for establishing, maintaining, and synchronizing communication between applications running on different hosts. Establishing a session means initiating communication between applications and negotiating the necessary parameters for the session. Data synchronization ensures that data is transmitted in the correct order and provides mechanisms for recovery in case of transmission failures. Examples of the session layer are network file system, NFS, and remote procedure call, RPC. Layer 6, presentation layer. The presentation layer ensures the data is delivered in a form the application layer can understand. Layer 6 handles data encoding, compression, and encryption. An example of encoding is character encoding, such as ASCII or Unicode. Various standards are used at the presentation layer. Consider the scenario where we want to send an image via email. First, we use JPEG, GIF, and PNG, GIF, or GIF to save our images. Furthermore, although hidden from the user by the email client, we use MIME, multi-purpose internet mail extensions to attach the file to our email. MIME encodes a binary file using 7-bit ASCII characters. Layer 7, application layer. The application layer provides network services directly to end user applications. Your web browser would use the HTTP protocol to request a file, submit a form, or upload a file. The application layer is the top layer, and you might have encountered many of its protocols as you use different applications. Examples of layer 7 protocols are HTTP, FTP, DNS, POP3, SMTP, and IMAP. Don't worry if you are not familiar with all of them. Summary. Reading about the ISO OSI model for the first time can be intimidating. However, it becomes easier as you progress in your study of networking protocols. To help with your studies, we have summarized the ISO OSI models in the tables below. All right, so you got layer number, layer name, main function, example protocol standard. So layer 7, application layer, providing services and interfaces to applications, HTTP, FTP, etc., etc. Layer 6, presentation layer, data encoding, encryption, and compression. So go through and make sure you have this information in your brain so you can remember it when the time comes. Okay, so you may have this in an interview question or something like that. So I recommend learning and understand which each layer represents and what it does. Okay, and let's see here. Question time. Which layer is responsible for connecting one application to another? Which layer is responsible for routing packets to the proper network? In the OSI model, which layer is responsible for encoding the application layer? Which layer is responsible for transmitting data between hosts on the same network segment. So go ahead and try to figure these out yourself, then come back to the video and we will continue on. Hey everybody, welcome back to my channel. Be sure to hit the like button, comment, and subscribe. Once you subscribe, be sure to hit that notification bell. All right, so you know every time I post a new video. As you can see here, most people that view my videos, view my channel, are not subscribed. Now, if you do subscribe, it will help me get into the YouTube algorithm so that we can continue to grow our glorious community here. As always, thank you all for taking the time to watch. Have a nice day and enjoy the video. Okay, let's take a look here. Which layer is responsible for connecting one application to another? That's going to be layer 4. Which layer is responsible for routing packets to the proper network? That's going to be layer 3. The OSI model. Which layer is responsible for encoding the application data? That's going to be layer 6. And which layer is responsible for transferring data between hosts on the same network segment? That's going to be layer 2. All right, let's continue on to task number 3, TCP IP model, and let's see what they say here. It says now that we have covered the conceptual ISO OSI model, it is time to study an implemented model, the TCP IP model. The TCP IP stands for Transmission Control Protocol, IP or Internet Protocol, and was developed in the 1970s by the Department of Defense, which is known as the DoD. I hear you ask why DoD would create such a model. One of the strengths of this model is that it shows or allows a network to continue to function as parts of it are out of service, for instance, due to a military attack. This capability is possible in part due to the design of the routing protocols to adapt as the network topology changes. In our presentation of the ISO OSI model, we went from bottom to top from layer 1 to layer 7. In this task, let's look at things from a different perspective, from top to bottom. From top to bottom, we have the application layer, the OSI model, application presentation, and session layers, i.e. layers 5, 6, and 7, are grouped into the application layer in the TCP IP model. Transport layer, this is layer 4. Internet layer, this is layer 3. The OSI model's network layer is called the internet layer in the TCP IP model. And link layer, this is layer 2. The table below shows the TCP IP models layer mapped to the ISO model layers. So you can see that here. All right, so go ahead and read through this, understand what's going on here. Many modern networking textbooks show the TCP/IP model as 5 layers instead of 4. For example, in computer networking, a top-down approach, 8th edition, Kuros and Ross describe the following 5-layer internet protocol stack by including the physical layer, application, transport, network, link, and physical. In the following task, we will cover the IP protocol from the internet layer in the UDP and TCP protocols from the transport layer. To which layer does the HTTP protocol in the TCP/IP model? Okay, so if we go back up here, and looks like going to be the application layer. So go ahead and put that in here. Okay, how many layers of the OSI model does the application layer in a TCP/IP model cover? 3 should be our answer here. Remember, if we scroll back up here, you can see that here. Application layer, the OSI model application presentation and session layers, i.e. layers 5, 6, and 7 are grouped into the application layer in the TCP IP model. All right, so we're done here. Task number 4, IP addresses and subnets. Let's see what they are talking about here. When you hear the word IP address, you might think of an address like 192.168.0.1 or something less common, such as 7 or 172.16.159.243. In both cases, you are right. Both of these are IP addresses, IPv4, IP version 4 addresses to be specific. Every host on the network needs a unique identifier for other hosts to communicate with him. Without a unique identifier, the host cannot be found without ambiguity. When using the TCP/IP protocol suite, we need to assign an IP address for each device connected to the network. One analogy of an IP address is your home postal address. Your postal address allows you to receive letters and parcels from all over the world. Furthermore, it can identify your home without ambiguity. Otherwise, you cannot shop online. As you might already know, we have IPv4 and IPv6, which is IP version 6. IPv4 is still the most common, and whenever you come across a text mentioning IP without the version, we expect them to mean IPv4. So what makes an IP address? An IP address comprises 4 octets, i.e. 32 bits, Being 8 bits, an octet allows us to represent a decimal number between 0 and 255. And IP address is shown in the image below. So you got the first octet here, second octet, third octet, and fourth octet, okay? At the risk of oversimplifying things, the 0 to 255 are reserved for or the 0 and 255 are reserved for the network and broadcast addresses respectively. In other words, 192.168.1.0 is the network address, while 192.168.1.255 is the broadcast address. Sending to the broadcast address targets all hosts on the network. With the simple math, with simple math, you can conclude that we cannot have more than 4 billion unique IPv4 addresses. If you are curious about the math, it is approximately 2 to the 32nd power because we have 32 bits. This number is approximate because we didn't consider network and broadcast addresses. Looking up your network configuration, you can look up your IP address on the MS Windows command line using the command ipconfig. On Linux and Unix-based systems, you can issue the command ifconfig or IP address show, which can be typed as IPAS. In the terminal window below, we use ifconfig, so you can just type in, whoops, IPA, right? Do that. Okay, you can do, and it'll show you information. Okay, so let's try what they're doing here. IPAS, same thing here, it looks like. Yeah, there we go. And let's go ahead and continue. The terminal output above indicates the following. The host laptop IP address is 192.168.66.89. The subnet mask is 255.255.255.0. The broadcast address is 192.168.66.255. Let's use IPAS to compare how the network card IP address is presented. Okay, so I wonder if ifconfig works on this machine. Oh, it does. Okay, awesome, cool. Let's see here. The terminal output above indicates the following. The host laptop IP address is 192.168.66.89/24 or CIDR 24. The broadcast address is 192.168.66.255. If you're wondering, a subnet mask of 255.255.255.0 can be written as a /24. The /24 means that the leftmost 24 bits within the IP address do not change across the network, i.e. the subnet. In other words, the leftmost 3 octets are the same across the whole subnet. Therefore, we can expect to find addresses that range from 192.168.66.1 to 192.168.66.254, similar to what was mentioned earlier. 192.168.66.0 and 192.168.66.255 are the network and broadcast addresses, respectively. Private addresses. As we are explaining IP addresses, it is useful to mention that the most practical purposes, there are two types of IP addresses. You got public IP addresses and you got private IP addresses. RFC 1918 defines the following 3 ranges of IP address, private IP addresses. You can see them here. You got the 10.0.0.0. All right, so you can see there, I'm not going to read them all off here, but you can see them here. We presented earlier an analogy stating that a public IP address is like your home postal address. A private IP address is different. The original idea is that it cannot reach or be reached from the outside world. That's right, it's not routable via the internet. It is like an isolated city or compound where all houses and apartments are numbered systematically and can easily exchange mail with each other, but not with the outside world. For a private IP address to access the internet, the router must have a public IP address and must support network address translation, which is NAT. At this stage, let's not worry about understanding how NAT works, as we will revisit it later in this module. Before moving on, I recommend memorizing the private IP addresses ranges. Otherwise, you might see an IP address such as 10.1.33.7 or 172.31.33.7 and try to access it from a public IP address. Routing. A router is like your local post office. You hand them the mail parcel and they will know how to deliver it. If we dig deeper, you might mail something to an address in another city or country. The post office will check the address and decide where to send it next. For example, if it is to leave the country, we expect one central office to handle all shipments abroad. In technical terms, a router forwards packets to the proper network. Usually, a data packet passes through multiple routers before it reaches its final destination, also known as hops. The router functions at layer 3, inspecting the IP address and forwarding the packet to the best network router so that the packet gets closer to its destination. And here's what that looks like here, or an example. All right. Uh, Answer these questions. Which of the following IP addresses is not a private IP address, and which of the following IP addresses is not a valid IP address? So go ahead and try to answer this yourself using the information, and then we will continue. All right, it looks like this is going to be the one that's not a private IP address. Okay, and which of the following IP addresses is not a valid IP address? It's going to be this one. Remember, we can't go over 255, and this one goes to 305 right there, so this is not right. Here we go. Task number 5, UDP and TCP. Let's see what they're talking about here. The IP protocol allows us to reach a destination host on the network. The host is identified by its IP address. We need protocols that would enable processes on network hosts to communicate with each other. There are two transport protocols to achieve that: UDP and TCP. UDP, which is User Datagram Protocol, allows us to reach a specific process on this target host. UDP is a simple, connectionless protocol that operates at the transport layer, i.e. layer 4. Being connectionless means that it does not need to establish a connection. UDP does not even need to provide a mechanism to know that the packet has been delivered. An IP address identifies the host. We need a mechanism to determine the sending and receiving process. This can be achieved by using port numbers. A port number uses 2 octets. Consequently, it ranges from 1 to 65,535. Port 0 reserved. The number 65,535 is calculated by the expression 2 to the 16th power minus 1. A real-life example similar to UDP is the standard mail service with no delivery information or confirmation. In other words, this is no guarantee that the UDP packet has been received successfully. Similar to the case of sending a parcel using standard mail with no confirmation of delivery. In this case of standard mail, it means a cheaper cost than the mail delivery options with confirmation. In the case of UDP, it means better speed than a transport protocol that provides confirmation. But what if we want a transport protocol that acknowledges received packets? The answer lies in using TCP instead of UDP. Right, like I said earlier, UDP is like streaming services like YouTube and stuff, right? Fire and forget. TCP is Transmission Control Protocol, which is a connection-oriented transport protocol that uses various mechanisms to ensure reliable data delivery sent by the different processes on the network host. Like UDP, it is a layer 4 protocol. Being connection oriented, it requires the establishment of a TCP connection before any data can be sent. In TCP, each data octet has a sequence number. This makes it easy for the receiver to identify lost or duplicated packets. The receiver, on the other hand, acknowledges the reception of data with an acknowledgement number specifying the last received octet. A TCP connection is established using what's called a three-way handshake. Very important here. Two flags are used: SYN, which is synchronized, and ACK, which is acknowledgement. The packets are sent as follows, okay? All right, send packet. The client initiates the connection by sending a send packet to the server. This packet contains the client's randomly chosen initial sequence number. Number 2, send ACK packet. The server responds to the send packet with a send ACK packet, which adds the initial sequence number randomly chosen by the server. Number 3, ACK packet. The three-way handshake is completed as the client sends an ACK packet to acknowledge the reception of the send ACK packet. And this is what it looks like here. Okay, send ACK, and then ACK. Similar to UDP, TCP identifies the process of initiating or waiting, listening for a connection using port numbers. As stated, a valid port number ranges between 1 and 65,535 because it uses 2 octets and port 0 is reserved. All right, question and answer time. Which protocol requires a three-way handshake? What is the approximate number of ports in thousands? All right, so go ahead and try to figure this out and then come back to the video. All right, so this one's going to be TCP. It says, what is the approximate number of port numbers in thousands? And this should be 65. Remember, if you go back up here, it's between 1 and 65,535. So 65,000 is the approximate number of ports. Okay, so that's going to be our answer. Task number 6 is encapsulation. So let's see what they're talking about here. Before wrapping up, it is crucial to explain another key concept, encapsulation. In this context, encapsulation refers to the process of every layer adding a header and sometimes a trailer to the received unit of data and sending the encapsulated unit to the layer below. Encapsulation is an essential concept as it allows each layer to focus on its intended function. In the image below, we have the following 4 steps. Application data. It all starts when the user inputs the data they want to send into the application. For example, you write an email or an instant message and hit the send button. The application formats this data and starts sending it according to the application protocol using the layer below it, the transport layer. Transport protocol segment or datagram. The transport layer, such as TCP or UDP, adds the proper header information and creates the TCP segment or UDP datagram. This segment is sent to the layer below it, the network layer. Network packet. The network layer, i.e. the internet layer, adds an IP header to the received TCP segment or UDP datagram. Then this IP packet is sent to the layer below it, the data link layer, data link frame. The Ethernet or Wi-Fi receives the IP packet and adds the proper header and trailer, creating a frame. We start with application data. At the transport layer, we add a TCP or UDP header to create a TCP segment or UDP datagram. Again, at the network layer, we add the proper IP header to get an IP packet that can be routed over the internet. Finally, we add the appropriate header and trailer to get a Wi-Fi or Ethernet frame at the link layer. And this is what they're talking about here. And you can see how they're adding stuff to it. All right. This process has to be reversed on the receiving end until the application is extracted. The life of a packet. Let's see what they're talking about here. Based on what we studied so far, we can explain a simplified version of the packet's life. Let's consider the scenario where you search for a room on TryHackMe. Number one, it says on the TryHackMe search page, you enter your search query and hit enter. Number two, your web browser using HTTPS prepares an HTTP request and pushes it to the layer below it, the transport layer. Number three, the TCP layer needs to establish a connection via a three-way handshake between your browser and the TryHackMe web server. After establishing the TCP connection, it can send the HTTP request containing the search query. Each TCP segment created is sent to the layer below it, the internet layer. Layer 4, or sorry, number 4, the IP layer adds the source IP address, i.e. your computer, and the destination IP address, i.e. the IP address of the TryHackMe's web server. For this packet to reach the router, your laptop delivers it to the layer below it, the link layer. 5. Depending on the protocol, the link layer adds the proper link layer, header, and trailer, and the packet is sent to the router. Number 6, the router removes the link layer, header, and trailer, inspects the IP destination among other fields, and routes the packet to the proper link. Each router repeats this process until it reaches the router of the target server. The steps will then be reversed as the packet reaches the router of the destination network. As we cover additional protocols, we will revisit this exercise and create a more in-depth version. All right, so that's quite a lot to take in there. So reread this if you're not understanding what's going on here. On a Wi-Fi, within what will an IP packet be encapsulated? What do you call the UDP data unit that encapsulates the application data? What do you call the data unit that encapsulates the application data sent over TCP? So go ahead and try to answer these and then come back to the video. So let's take a look here. On a Wi-Fi, within what will an IP packet be encapsulated? That's going to be frame. What do you call the UDP data unit that encapsulates the application layer? That's going to be datagram. What do you call the data unit that encapsulates the application data sent over TCP? That's going to be segment. So, right, so if you go back and scroll up again, you can see that information in here. It's talking about encapsulation, okay? So be sure to read through that again. And let's go ahead and continue on to task number 7 and Telnet, okay? I already have both machines started up here. Okay, so start the tack box, show split screen, which you have it right there. Once the two machines are ready, we need to start the terminal on the attack box to experiment with Telnet. The Telnet, which is Teletype Network Protocol, is a network protocol for remote terminal connection. In simpler words, Telnet, a Telnet client, allows you to connect to and communicate with a remote system and issue text commands. Since although initially it was used for remote administration, we can use Telnet to connect to any server listening on a TCP port number. On the target virtual machine, different services are running. We will experiment with three of them. Echo server. This server echoes everything you send it. By default, it listens on port 7. Daytime server. This server listens on port 13 by default and replies with the current day and time. Web HTTP server. This listens on TCP port 80 by default and serves web pages. Before continuing, we should mention that the Echo and daytime servers are considered security risk and should not be run. However, we started them explicitly to demonstrate communication with the server using Telnet. And the terminal below, we connect to the target VM at the Echo server TCP port number 7. To close the connection, press the control and the it's like a closing bracket keys simultaneously. All right, so let's go ahead and take a look here. Go ahead and clear all this junk out of here. And I'm going to copy and paste. So you got Telnet, the target, right? Target machine, and then the port. So that's the syntax. All right, so let's go ahead and copy and paste this over. Okay, I copy and paste it in there. You got Telnet, target IP, and then the port we're targeting, which is 7. And I did the same thing as they're doing here, okay? And it says to close out of this, or to get out of this prompt here, you can hit control and then the closing bracket, and then type in quit, and now we're back. All right, and the terminal below, we use Telnet to connect to the daytime server, listening at port 13. We notice that the connection closes once the current date and time are returned. All right, so I'm gonna clear all this out, and then I'm gonna up arrow, and just change 7 to 13 to connect. Okay, there we go. Finally, let's request a web page using Telnet. After connecting to port 80, you will need to issue the command get HTTP 1.1 and identify the host where anything goes, such as host, then telnet.thm. Next, you need to press enter twice so your last input line is a blank line. The output below shows the exchange. The page has been redacted. You may have to press enter after sending the information in case you don't get a response. All right, so let's go and try this out. Clear and then change this to 80. Okay, now we have to do this here. So copy and paste. All right, then the host information here. Okay, and then we need to do that. Okay, there we go. Looks good. There's the flag. So I'm going to go ahead and grab it because we're about to enter it somewhere. Awesome. Use Telnet to connect to the web server on 10.10.10.172.61. What is the name of the version of the HTTP server? And then what flag did you get? So I'm going to type this flag in first. And what's the version of the server? Okay, so let's take a look here. It looks like it's going to be light TPD version 1.4.63. So let's go ahead and grab that information here and plug it in. So this is also known as banner grabbing, okay? You can do that with Telnet to see what's behind that port. You might get some information like this. Task number 8, conclusion. In this room, we covered the ISO, OSI, and TCP IP models, comparing and contrasting the two. We also covered IP addresses and subnets, briefly explaining routing. Furthermore, after diving into TCP and UDP, we explain encapsulation. For demonstration purposes, we use Telnet to talk to different servers over TCP. Now that we have finished networking concepts, it is time to join networking essentials. Please note and remember all the concepts, network layers, and protocols explained in this room. Okay, hope you guys took good notes here and paid attention. So we're done with this room here. And if you enjoyed the video, be sure to hit that like button, subscribe to the channel if you're new here. share the video, comment below your thoughts and opinions on the information shared in the video. As always, thank you all for taking time to watch my video. Have a nice day, and I will see you later.